Hello, I'm Mrs. Edwards, and today we get to find derivatives from a graph and from a table. But before we do that, I'm going to give you some really strong notational recommendations. Okay, there are three different instances that I'm going to share with you where you see this notation and you should immediately switch to another notation. It's just not conducive to doing calculus. Okay, one of them is the location of the exponent. When that exponent in this case is kind of stuck in there, you want to remove it and rewrite this as sine of x to the third power. This is a nice time to introduce this change in notation because you have just found out how to do the chain rule. And the chain rule really relies on you identifying that input function, that ugly function, something that's other than plain x. And so an easy way to really identify the input function is to show that input function inside of parentheses. Okay, so here's another place where I would say that exponent is misplaced, but you see it like this often. Okay, so I'm going to rewrite that as f of x to the power of 4. This does not mean the fourth derivative of, kind of a subtle difference. Remember when you have the fourth derivative, they would put the 4 in the exponent spot, but it would be inside of parentheses. Okay, so this is f of x to the fourth power. This one I would rewrite as g of x to the negative 2. And here I would have h of 9x plus 1 raised to the third power. Okay. Next, the type of notation that I would immediately change is composition notation. If you see f composition g of x, that really means to go into the f function, replace every x in the f function with the g function. So replace the x's with the g function. This notation is much better. Okay, this is emphasizing that g of x there is that input function. Okay, so on this one, if I rewrote it, it would be g of f of x. Or let's say this one, this would be f of g of 8x. All right, the next type is root form. You do not want to leave things in root form. If you want to rewrite your final answer in root form, great. But as soon as you see root form, you want to change to exponential notation. So the exponent on x inside there is to the first power, and the little number that we don't see on the outside of the root is 2. So when you go to exponential form, I think of it as inside out, like flip a shirt inside out, and that means that the exponent on the inside goes over the exponent on the outside. All right, so that's going to be to the 1/2. And here, that would be 3x plus 4 raised to the 1/2 power. Here, we'd have x plus 4 raised to the 1/3. And then here, that x minus 1 raised to the 2/3. Okay, so just kind of take a moment there. Look at that one more time. We have a misplaced exponent. We have composition notation. And we have root notation. And we want to immediately, when we see these types of notation, change it over to emphasize that input function so that we know when we're taking a derivative that what's inside parentheses is what we chain on the derivative of. Okay, so let's get started. Here we have a couple of graphs. We have the graph of f of x and the graph of g of x. And we want to fill in this table with the answers to the functions and their derivatives at some x values. So let's start with a couple of easy ones. Okay, right here, if I want to evaluate the function f at 0, well then I'm going to go to 0 on the x-axis on the f function. And when I go up and I hit the curve, the height is 3. So when I plug 0 into the f function, I get out 3. Okay, here's another rather easy one. I substitute 2 into the f function. So if I substitute 2 into the f function, I end up getting a y-coordinate of 2. So my answer is 2. Okay, let's go over to the g function. A couple of easy ones there. If I substitute -3 into the g function, When I go till I hit the curve, I'm going to be down there at -2. So I substitute -3 and I get out -2. Let's evaluate the g function at 0. So if I substitute 0 into the g function, I end up getting a height of -2 as well. Okay, and then let's say I substitute 2 into the g function. Okay, and I end up getting a height of 1. So when you substitute a number into a function, you're just looking for the height at that x value. Now, a few of these that we skipped are a little bit more challenging because they don't have a nice, neat height, I should say. So if I substitute -3 into f of x, see how I can't tell exactly how low we are, like what is that coordinate? Now I could estimate, and sometimes that's okay, but let's say I want to know the exact value. Well, if I want to know the exact value, then what I can do is I can figure out what's the equation of the line that this point is on. To write the equation of a line, you just need the slope and the y-intercept. That's at least one way that we can find it. And it's kind of nice in this line here because we can clearly see that the y-intercept is at 3. So we know we're going to have +3. Then let's look for the slope. All right, if I go to -2 right there, it's crossing at a nice, neat point. So starting here, if I go up 3 and over 2, rise 3, run 2, and my y-intercept is 3, there's the equation of that line. Now, if I couldn't tell where the y-intercept was, I would have to find 2 points that I could tell and subtract the y's over the x's to find the slope, and then I could do y minus the y coordinate equals slope times x minus the x coordinate and eventually get to the line. Okay, now that we have the equation, it's not so difficult to find out what's the answer to f when I plug in -3. So if I do 3 over 2 multiplied by -3 and then add 3, I'm going to get -1.5. All right, here's another one. If I substitute in 1 into the f function, again, I'm not at a really nice, easy place for me to tell what my y-coordinate would be. So I need the equation of that line. Now, looking at this line, see how the y-intercept is 3? We're crossing the y-axis at 3, so my b is 3. Now let's look for slope. If I start up here at the y-intercept, and then I go down 1, forwards 2, I can tell that my slope is -1/2. So we're going to have y equals -1/2 x plus 3. Now I'll just substitute the 1 into this function. -1/2 multiplied by 1 is -1/2 plus 3 is 2.5. Okay, let's do the same thing over here for g. We only had one missing one. If I substitute 1 into the g function, and I can't tell exactly what the height is, so we want the equation of that piece of g of x, the equation of that line, and it is crossing the y-axis at -2, so our y-intercept is -2, and then let's find the slope. So if I start here at the y-intercept -2, I could rise a total of 3, 1, 2, 3, and run 2, so my slope is 3 over 2 with a y-intercept of -2. Okay, so now I can substitute 1. I want to find g of 1, so if I plug in 1, 3/2 times 1 is 3/2 or 1.5, and 1.5 minus 2 is -0.5. Now that we've evaluated the functions at -3, 0, 1, and 2, okay, let's just pause to collect your thoughts. One way that we could evaluate was to simply look to the x-axis at that x value, go up or down till we hit the curve and say, what's the y-coordinate? And sometimes that y-coordinate is obvious. But if it's not obvious and we're on a line, we need to figure out what's the equation of the line containing that point. And once we have the equation, we can now substitute it into that function and and then we'll have our answer. Okay, next we want to evaluate the derivatives at these x values. Let's start with a couple of easy ones. G prime of x. If I evaluate g prime of x at -3, that is not the y coordinate, right? The derivative means the slope of the tangent at that x value. So I'm here on the g function at -3, and the slope of the tangent to that point, well, it's going to be a horizontal tangent, and so we're going to have 0. Okay, how about this one? If we want to evaluate g prime of 0. So I go to the g function at x equals 0, and it is not the y coordinate. We're saying what's the slope of the tangent at that point. Now I'm going to just go back there for a second so you can really see it. See how at that location there's a cusp, there's a sharp spot? The slope of the tangent does not exist because when you're on a cusp, a sharp point like that, a corner, that tangent line, it would teeter. You can't get a unique one. So derivatives do not exist at cusps. So that one is undefined. Okay, how about the derivative of g at both -0.5 and at 1? Okay, so we're going to do those at the same time because both at x equals -0.5, at x equals 1, my bad, over here, x equals 1 and x equals 2. Okay, so here's 1 and here's 2. Both of these points are on the same line. And the slope of the tangent to a line, the derivative, is the same as the slope of the line. And we already wrote the equation, so we can see that the slope there is 3/2. And so the answer to both of those is 3/2. All right, then let's come over here to f, and let's find f prime evaluated at 0. Well, f prime at 0, notice we're at a cusp. Okay, so the slope of the tangent does not exist there. The derivative of f at 0 is undefined. Okay, then let's evaluate the derivative of f at -3. So if I go to -3, the derivative is the slope of the tangent at that point, not the y coordinate. What's the slope of the tangent? Well, anywhere that we are on this line, the derivative of any point that's on that line is going to be the same as the slope of that line. So the slope at x equals -3 is 3/2. Okay, then evaluating f prime at 1 and at 2, we can do those simultaneously, okay, because at x equals 1 and x equals 2, these points are on the same line there. And so the derivative at those points is the slope of the tangent there. And the slope of a tangent to a line is the same as the slope of the line. So we get -1/2 for both of those. Now that we have evaluated a handful of points, we're going to use this table to then evaluate some further derivatives. So we went through and evaluated the f function and g function and their derivatives at a handful of x values. I did that because I just wanted to have that piece done, so now we can focus on the notation of a handful of problems. So we're being asked here to find f plus g evaluated at -3. What that came from is we are replacing the x with -3. Now f plus g of x really means f of x plus g of x. So if we're going to evaluate f plus g at -3, we're just replacing those x's with -3, and we already found the heights to the f function at -3 and the g function at -3. So if we look there in our table, we got -1.5 and -2 combine, and our answer is -3.5. All right, here's another one. We want to find f plus g prime evaluated at -3. That came from substituting -3 in for x. Now, what is f plus g prime of x? What was that the derivative of? Well, that was the derivative of f plus g of x. I really don't like the notation f plus g of x, so let's rewrite f plus g of x. That just means f of x plus g of x. So if I want to take the derivative of f plus g of x, that's the same thing as taking the derivative of f of x plus g of x. There is not a special rule for derivatives, right? For addition and subtraction, you just take the derivative. So the derivative of f of x plus g of x is f prime of x plus g prime of x. Now we're ready to substitute -3 into our derivative. Go to our table, and we already found the slope of the tangents of the f function and g function at -3. So looking there in our table, we found out the answers were 3/2 and 0. Combine, and our final answer is 1.5. Using the same information, let's evaluate f times g of 1. Well, what did that come from? That was 1 substituted in for x in f times g of x. Now, I don't care for the notation f times g of x. That really means f of x multiplied by g of x. So in other words, we're just going to substitute 1 in there for x. So our answer is going to be f of 1 multiplied by g of 1. Looking up in the table, because we already found the answers to the heights of the f function and g function at 1, we had 2.5 and -0.5. So I'm going to pop those in there. And when I multiply, we end up getting -1.25. Now let's find the answer to f times g's derivative evaluated at 1. F times g's derivative. So let's just backtrack a little bit. F times g prime of 1 is f times g's derivative of x evaluated at 1. Now, what was f times g's derivative? What was it the derivative of? Well, it would have been the derivative of f times g of x. Let's rewrite f times g of x in a little bit different way. F times g of x really means f of x times g of x. So taking the derivative of f times g of x to get f times g prime of x is the same thing as taking the derivative of f times g. And when you are multiplying and you're finding a derivative, we do have a special rule for finding the derivative of two things multiplied together that have x's in them. We have to use the product rule. So we are going to have f times g prime plus g times f prime. Now, some of you can go directly there and you're okay. You're saying the derivative of f multiplied by g is f times g prime plus g times f prime. Okay, now let's substitute 1. We already evaluated from the graph the heights of f and g at 1 and the slope of the tangents of f and g at 1. So looking in the table there for answers, replace them, do some simplifying. 2.5 times 1.5 is 3.75. -0.5 times -0.5 is positive 0.25. Combine, and I end up getting 4. F composition g of 2. So f comp g, I did not like that notation. So let's go back a bit. We have f comp g of x, but that is really f of g of x. All right, so let's substitute 2. Go into our table and find the answer to g of 2. So looking across there, g of 2 is 1. Now we can find f evaluated at 1. So going across from 1 until we get to the f function, that's 2.5, and there's our answer. Now let's evaluate the composition f comp g's derivative evaluated at 2. That came from the composition's derivative of x. Now what does that really mean? Okay, that derivative was the derivative of f comp g of x. I do not like the function f comp g of x. I don't like the way that's written. So that really means f of g of x. So if I take the derivative of f comp g of x and I get f comp g prime of x, taking the derivative over here on the left is the same as taking the derivative on the right. So let's focus on what is the derivative of f composition f of g of x. If this was just f of x, the derivative of f of x would be f prime of x. But rather than being just f of x, we have f of an input function, f of ugly. All right, so if we have f of an input function, the derivative is f prime of the input function chain on times the derivative of the input function. So f prime of ugly times the derivative of ugly. Okay, so f prime of g of x times g prime of x. Now I'm going to substitute in 2, go to my table, and I can find the answer to g of 2. G of 2 was 1. I can also find the answer of g prime of 2. That was 3/2. Now I'm ready to find the answer to f prime of 1. Okay, and looking there in the table, f prime of 1 was -1/2. Now if I take -0.5 multiplied by 1.5, I get -0.75.